Well, hello and welcome back to Engineering 211 Statics, and I wanted to work on the second sample exam. So if you're preparing for the second midterm exam, this will hopefully be a good activity. The one thing that I would caution you is that you've tried this on your own before you watch this solution. So if you go to the website, and that link is at the in the description of the video here, you can go and click on the Engineering 211 folder, and then there's a subfolder under that, or a subpage under that, that has sample exams. And if you go there, you can look at the second exam that has the just the exam without the solutions, and there's another file that actually has the second exam with the solutions, and a lot of those are going to be what I'm going over today, and I may be adding some information as I go along. But again, I've warned you in the past that if you haven't done that, I would highly recommend you do that before watching this video. Go ahead and pause this video, print that test out, give it a shot before watching this video. So I'm figuring that you've tried it on your own, and we'll go forward from there. So question number one, we've got a typical truss problem. It says that takes the length of each member as 12 feet, and I realize the verbiage doesn't show up very well on the video. I've tried to blow it up some. If you go and you download the test, and I'll also be posting the PDF, so you should have access to pretty good resolution, and I'll try and reiterate these values if you're just watching the video. Then the load here is 5,000 pounds. We're going to assume that the members are negligible mass and are pin connected, so we've got our typical truss arrangement. And it looks like we're doing questions 1, 2, and 3 off of this scenario. So let's see what we're looking for. We're looking for the force in member BC, so that's this one up here. The member in BE, so that's that one there. And then I think if we go to the third question, it's always a good idea to figure out what they want so we can get it in the fastest way. They want AE, so that's going to be this one. So I think with that, what I'm going to do is I'm going to say that I'm going to section off this thing. I'm going to slice a section right through there. I'll have 1, 2, 3 unknowns. Those 3 unknowns are the unknowns I'm looking for. It should be pretty efficient. Well, whether we do method of joints or method of sections, we're going to have to get this reaction over here, A. So let me do that. So this would have been back to just plain old equilibrium, not even structural work yet, because we're just finding the reactions. So we're going to have some AY and some AX. Then there'll be the roller with D over here. And we have at the middle of this thing, we have this 5,000 pounds acting down like that. We're told that each is 12 feet, so this is 12 feet, this is 12 feet, and we should probably deal with this height. What's that going to be? That's going to be, if I look at one of these triangles, it's equilateral triangle, right? If this is 12, 12, and 12, then this becomes, what, 60 degrees? So I could say that this is 12 times the sine of 60 degrees, which gives me 10.39 feet. Let me double check that so I don't propagate a mistake through the problem. Yeah, 10.39. So I don't know that we need that yet, but in our preliminary work. So I'd like to find this AY, so I think I'll sum the moments about D, setting that equal to 0. Maybe we'll take counterclockwise as positive. So we'll have 5,000 times the distance 12 minus AY times the distance of 12 plus 12 would be 24. That comes from 12 plus 12. And then AX is going to intersect that point. And, whoops, I'm summing it about D. Yes, so AX is going to intersect that point, and D is obviously intersecting that point, so all I should have to worry about is those two forces. So I can say that AY is equal to, moving that to the other side, 5,000 times 12 divided by 24. And a lot of you looking at the symmetry of the problem, the symmetry of the loading, the symmetry of the members would recognize that that's just half of 5,000, 2,500 pounds. Okay. Now, had someone come up here and put a force off of it up here like that, then that wouldn't be true at all, or had different geometry, that may not be true at all. The other thing that I can do is I probably need to get AX. Some of the forces in the X direction is equal to 0, which is equal to AX, because that's the only thing I have in the X direction. And again, had you had a force in the horizontal, it'd be a different story. So now that I've got AX defined and AY defined, I'm going to go ahead and do this section. I'm going to get a different piece of paper to do that. And I'm going to build this section. So I have the point here A, remember, I'm going to call this, I'm going to assume that I have tension in the bottom, and that's going to be, looking at this picture, that's the AE. And up here, maybe I'll give myself a little more room, up here, I'm going to say that this BC is in compression. BC is in compression, and then I'm going to take this AE, and I'm going to say that's in compression. Let's see, I've got that. I think I'll be consistent with the solutions that we've gone through. So I'm going to draw that in tension. Okay, so AE is in, that's not A, this is, I'm messing this up. There's A, and there's B, so that's BC, and this is BE, isn't it? There we go. Now, okay, so I've got BE in tension, and AE in tension. Now I've got to put the reaction here. I just found that that was 2,500 pounds. And this one in the horizontal, that was 0, so I could just note that that's 0. Well, let's see. I should get that this distance here, didn't we have that already? That was 10.39. And I think we can go through there. So I think what I'll do is if I look at this point over here, E, if I sum the moments about E, setting that equal to 0, what do I come up with? Well, I have this 2,500 times what's the distance from A, there's A, to E right there. That's the 12 feet, isn't it? So I'm going to have 12. And that's going to tend to rotate it that way, so I'll go ahead and take that as positive. And then I'm going to have to subtract off BC, acting through this 10.39. Do I have anything else? No, I don't think so. So I can solve for BC is equal to 2,500 times 12 divided by 10.39, which gives me 2,887. I've got too many significant figures, but I'll leave that there. Now that was a positive number. How did we draw BC? We drew this in compression, didn't we? So if it's positive, that would affirm that it's compression, so I could say that BC is equal to 2,887 pounds in compression. Okay. Again, I have too many significant figures there, but we'll see what the answers hold. Maybe they have too many significant figures too. So we've got this one done. Now what could we do? Well, what if I sum the moment about B? So summing the moment about B, setting that equal to 0, BE and BC intersect that, so I should be able to get AE. So I can say that I have AE times a distance of 10.39, and we'll take that as positive. And then I have to subtract off 2,500 times the distance it acts through. Now, if this is an equilateral triangle, this is going to be what? Half of 12. That's going to be 6, isn't it? So I'll have times 6. So I can solve for AE. I think that's all I've got because I'm some of the moments about there. I just have this force and that. So doing a section on this was very efficient. AE is equal to 2,500 times 6 divided by 10.39. $1443.6, we'll call it 44. Again, I got too many significant figures there, but we'll leave that. So this is a positive number. How did we draw AE? We drew it in tension, didn't we? So that affirms that AE is equal to 1,444 pounds in tension. Okay. And lastly, we've got AE, so we've got that one. So we need BE. What would be a good way to get that one? Probably just quick summing the forces in the vertical direction, setting those equal to 0. What do I have? I have 2,500 acting up. That one's horizontal, that one's horizontal, so I just have to subtract off BE times what? Well, let's see. If I have 60 in there, this is going to be 30, isn't it? So I could just say cosine 30 degrees. And if you're looking in the solutions, I think I said the sine of 60, which those would be the same value. So we've got that BE is equal to, let's see, as the vertical, I was taking up as positive for completeness sake. Yeah. Okay, so I've got BE is equal to 2,500 divided by the cosine of 30, which gives me 2,886.75, we'll just say 87 pounds. And again, we drew BE in tension, so that was in tension. It's positive, so that indicates that BE is definitely going to be 2,887 pounds in tension, because we got a positive. We drew it in tension, we got a positive number. Now, I had started to draw it in compression. What if I had drawn it in compression? Well, let's see, what would have happened? We would have had a positive number here, wouldn't we? Okay, and then when that came over, this would have been a negative number, and we would have said it was opposite of compression, which is tension. So again, if you're careful and consistent, it doesn't matter. I don't want to say it doesn't matter in a flippant sense, but as long as you're consistent and careful, it will take care. So let's look at the answers. What was BC? 1287 in compression, 1287 in tension, 1287 in compression. So it looks like answer C there. What about BE? We had, was I saying 1287? 2,887, sorry about that. 2,887 was BC, and it was in compression. So we've got that one. Double check that. I'd be ashamed to circle the wrong one. And then what do we get for BE? Again, 2,887, 2,887, and this one's in tension, so that would be A. And sometimes knowing whether it's in compression or tension is more important than the magnitude. And let's finish this up. I'm actually going to put this as, this will be page number 2. I'm going to say this is page number 4. On, we wanted AE. What is AE? 1444 in tension. And this is good. We've got 1443 in tension. Anything else that's better? No, 1443 compression, that's no good. So I'm going to take it like this. I would definitely not use none of the above. That's not what none of the above is for. Whether we have 1444 or 1443, that's the 1443 is obviously the right answer. Where could this have got astray a little bit? Probably in this number right here, depending on whether you keep that in the memory of your calculator or not. So I'm not going to play that game where we put down an answer 1443 and then we put down 1444 and try and get you to sort that out. So don't be tempted to use E in that case. Well, the other thing that I wanted to mention on this and why I wanted to put a separate page in here, let me double check those answers, C, A, and B. Good. Or what are we going to put on page 3? Well, on page 3, we could have done this with method of joints. So if I would have gone back with joints, we'd have something like this. At A, we would have had 2500. And then I would have had AB, probably in compression. And then AE, this is what, 60 degrees. This is 0, right? Is that what we had going at A? Yeah, 0, those two. So we would have got AE with that. And then what would we have had to have done? Probably gone on to do, so this is at A, and then we'd have to do at B. What would B look like? Well, I'd take this AB up there. There's AB. So I got that from here, and I brought it over to there. And then I would have had BE. BE and BC. And this is 60, and that was 60. So could we do this? We have two unknowns here, some of the force in X, some of the force in the Y. Absolutely. We could have got this one, and having found then this one, transferred that over here. Now when we got here, we'd have two unknowns, BC and BE. We would know this one. Could we have started with B? No. We've got three unknowns. We would have had to have gone back here and done something else. So you could have done this, and maybe some people would be more comfortable doing it with method of joints. I think method of sections is probably a little bit faster, but this would be good practice. You may want to try this, and the nice thing about it is you should get exactly the same answers for BC, for BE, and for AE. You'll be able to check to see whether you got it right. Double check that we don't have any loads elsewhere. Yeah, so that's what that would end up being. Okay, so that was page number 3. Most people have quite a bit of time on the exams, so you could probably try that with 2 different methods. Get the same answer and start to have a lot of confidence in your answers. Well, the next problem says to use the following figure to answer questions 4, 5, 6, and 7. And what are 4, 5, 6, and 7 about? 4 is we'd like the vertical reaction at A, so we're looking for that. What is the reaction at B? There's only one reaction at B, so we're looking for that one. What's the internal shear just to the right of B, and what's the internal bending just to the right of B? These two, we'll go ahead and go through these, but depending on where the exam falls time-wise in the term, how the holidays are in the term and whatnot, that may or may not be on the exam, and I would refer you to the information the week of the exam that will tell you what is covered. So we'll go ahead and go through this, but it may or may not be on the exam. So we've got a distributed load. We're told that the length is 10 feet there, and this length is 10 feet. Anywhere we see L, that's 10 feet, and we've got then 300 pounds per foot. Pounds per foot. So what I'm going to do is I'm going to do a free body diagram of this thing, see if I can find those reactions. So let's do that. At A, I have AY, I have AX, and I've got this load there like that, and we have this one like that, and we have B, and this is 10 feet and 10 feet and 300 pounds per foot. So I could look at this really as two equivalent loads. This one is going to be at the centroid of that rectangle, and this one's going to be at the centroid of the triangle. And this one's going to be what? 300 times 10. It's the area there. And it's going to be located halfway over, which would be at 5. And then this one's going to be the area of this triangle, 300 times 10 divided by 2, and it's going to be located at 1/3 of the distance, right? So if I were to sum the moments about A, setting it equal to 0, let's go ahead and take clockwise as positive. We have 300 times 10. That's the force, 300 times 10, because you take 300 pounds per foot, you multiply by 10 feet, you end up with a force. So this has to be multiplied by a distance. What distance is that? That's that 5. And to that, I'm going to add 300 times 10 over 2. And again, that's a force. That's the area. And what distance do we have? Well, we're going to have 10 plus 1/3 of 10. So 10 plus 10 over 3 gives me what? $13.33. Probably should have known that. So I have 13.33. Okay. And then I've got to subtract what? B times the distance that is acting through of 10. So I can solve then for B, which is going to be equal to 300 times 10 times 5 plus 300 times 10 over 2 times 13.33. And this is where that 13.33 comes from. We have to divide this whole thing by 10. So B is equal to okay, what does B turn out to be? 3,499.95. 3,499.95, let's just call that 3,500. And had I kept this in the memory of the calculator, I would have got 3,500. So B is 3,500 pounds. And we took this going up. It's a positive number, so this really means that it is going up, doesn't it? Okay, it's going up. So what is the reaction at B? 3,500 up. Well, we got to come back and do A, don't we? If you want to do A first, then you would have summed the moments about B. I think it's probably easier to sum the moments about A and then sum the forces in the vertical direction, setting those equal to 0. What do we have? AY plus B minus 300 times 10 minus 300 times 10 over 2. Now I substitute in my B as 3,500, and we get that AY is equal to, see, that's negative and that's negative, so when they go over there, you're going to have 1.5 times 300 times 10 minus 3,500. We get 1,000. AY turns out to be 1,000 pounds. We got a positive number. AY is pointing up, so we'd expect it to be 1,000 up. Okay. So we've got answer D. We've got answer B. What if you wanted AX? You have to be careful. Some of the forces, this wanted vertical, but if we wanted horizontal, some of the forces in the horizontal is equal to 0, which is AX. That was 0. Could we have got this AY a different way? Yeah. You could have got AY with summing the moments about B. And you might want to try that. So we could say try AY by summing the moments about B and setting those equal to 0. Because if I sum the moments about B, the only thing that I would have in the equation would be, or the only unknown I should say that I have in the equation would be AY. I'd have this force times that distance. Then I'd have to subtract off this force times this distance. And then I would have AY times that distance of 10. So I'd be able to solve for AY there, and it should be that answer. So you can go through that and check that on your own if you wish. Well, questions 6 and 7, like I say, sometimes depending on where we are in the term, we may or may not get to that. That's internal shear and bending. And it says, what is the internal shear force just to the right of B? So if we think of just to the right of B, we're going to talk about taking a section right through here. So that section looks like this. I'm going to cut through that beam. And I will have cut through the load. Okay, so this will be 300. And then my sign convention is called deformation sign convention. I have shear up, and I have moment, bending moment that's clockwise. Okay, because if I cut through a beam, the sign convention is this. If I look at the left-hand side, the shear is down, the moment is counterclockwise, and if I look at the right-hand side, the moment is up. Excuse me, the shear is up and the moment is clockwise, so that when I put those two together, they cancel each other out. So if I'm looking at this right-hand side, I have to put this convention on here so that my answers will match. Okay, because you notice our answers are positive and negative. So I got to figure out whether we're going to get a positive or negative, and I want to base it on a standard convention. Okay, so if we've sliced it just to the right of B, so it's just a tiny, tiny little distance to the right of B, that would mean that this distance here is still 10 feet, right? And if you want to say it's 9.99999 and keep going with the 0.9s, that's fine. It's about 10 feet. Okay, so if I sum the forces in the vertical, taking up as positive, what am I going to, I'm going to set that equal to 0. So what am I going to come up with? That's going to be equal to V. And then I have to subtract off this, don't I? So I'm going to have minus 300 times 10 divided by 2. That's the area there, right? So I could say that V is equal to what? 1,500 pounds. Would be equal to, because this is your equation, this is equal to 0. That's your equation. So this would be positive. So internal shear. This is our shear. Our internal shear, positive 1,500. So we have answer B. And that's why it's important we use this convention, because negative would be wrong. Okay. So what's the bending moment? Well, what we're going to do is we're going to sum the moments right at the cut points, setting those equal to 0. Why don't I go ahead and take clockwise as positive? So I'm going to sum the moments right about this cut. And really, I've only moved these over for clarity. And if I were to be more honest in this picture here, the shear force would go right through this, and the moment would be something like that. So the cool thing about doing it about the cut is I don't have to worry about the shear force. So if I got this wrong, I still stand a chance of getting the right answer here. So what I'm going to have is I'm going to have M, got to add that moment in, and then I have that force there, so I'm going to have plus 300 times, because isn't this 300 times 10 divided by 2. Yep. And then it acts through some distance. That's 1/3 of 10. That's the distance that it's acting through there, right there, that distance right there. So I could say that m is equal to, turns out to be a minus minus 5,000. And again, the negative have to be, that comes from this convention. So minus 5,000, that would be this one right there, D. Okay, so let me double check my answers here. For 4 and 5 we got D and B, 6 we got B, and 7 is D. Good. Okay, and like I said, sometimes we cover this and sometimes we don't. It depends on the term and where the holidays are, and you can look at the material that will be on the exam. That's usually posted at the week of the exam to see if we're going to do that. If we don't have this question on here and we don't have that question on there, what will you want to study? Well, we could ask other questions here. I mean, we could ask more questions about this. Oh, right here. There's an easy question. You could add on to it. Or other questions, we could do more trusses, or we could do more machines and things like that. Okay. Well, speaking of machines, let's go to this last one. No, I guess it's not the last one. Close to the last one. So we have a problem here. We've got a pin connection. We're told that this is 10 feet, this is 10 feet, this is 10 feet, and F is 1,000 pounds. See, if L is 10, this is 5 feet, this is 5 feet, this is 1,000 pounds, and the moment is 250 pound-feet. So how do you do a problem like this? Well, what you're going to want to do is you're going to want to take this thing apart. Technically, it's not a truss. Okay, so that means it's a frame or a machine. And if I look at removing the reactions, it is non-rigid. Okay, so that means I'm going to take it apart. So what I want to do is I want to look at this little right-hand side. So I have this pin here. And on the right-hand side, I have something that looks like this. Over here at point D, I've got that load there. We've got this moment, 250 pound-feet. I've got a load of 1,000 pounds. 1,000 pounds, remember, is a kip. That's an FYI. FY. FYI, 1,000 pounds is a kip, just in case it's used. Now let's see, we're going to have 5 feet here, 5 feet here. What do we have going on with the pin? Well, pin will support a force in 2 directions. I'm going to say that this is CY, and we could have CX if we wanted to, right? Okay, so I've modeled the pin with those 2 forces. I've got that one, I've got that one. We should be able to do this, right? So what are we looking for? We're looking for the, what's the reaction at B? So we're looking for this force here. What's the reaction at D? So we're looking for that force there. And I guess that those are the only 2. So, well, before we get done, we're going to have to get CY, because I've got to get CY figured out so that I can come back over to this beam and get B. But let's first start by summing the moments about C, setting that equal to 0. So I'll say that I have 1,000 times 5, 1,000 times that 5. Clockwise is positive, summing the moments about that point. Then I'm going to have to subtract off D times 10. So that's D times 10. And then I'm also going to have to add what? 250. So I've taken care of this one. It's a free vector. No matter where I sum the moments, about whether I sum it here, 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 or some point off the body, that's what I'm going to have. Then, so I've got that. I've got the D. I've got that one. And I've got that one. Yep, we should be good. So we could say that D is equal to 5,000 plus 250 divided by 10, right? So what's that turn out to be? 5250, 525, is that right? I think so. Double check that, shouldn't. Okay, yeah. So 525 pounds. We've shown that going up. It's a positive number, so that affirms that it's going up. So what's the reaction at D? 525 pounds up. What if we would have forgot this? If we would have forgot this guy here, we would have been trying to get this answer here. So that wouldn't have been good. 525 up. Now I said that I needed to also get CY. So let me sum the forces in the vertical direction, setting it equal to 0. I'll take positive up here. So I've got CY minus 1,000 plus D, which is this 525. So I could say that CY is equal to 1,000 minus 525, which gives me 475, doesn't it? Okay, 475 pounds. And that's going to be important when I go to this other piece. Now I have to switch pages to do that. Let me catch up on my page numbering. What did I have back over here? That was 4. This must be 5. Then 6. And 7. Let me grab a clean sheet for 8. So the CY is 475, and if I sum the forces in the horizontal direction, setting them equal to 0, I just have CX, don't I? So we'd recognize that's 0. So I'm going to take what I've learned about that at CY and apply it to a free body diagram of this left-hand side. Let's see how that works. So free body diagram of the left-hand side is going to look something like this. At A, I've got AX and AY. Then at B is a roller. So I'll just have B like that. We've got 10 feet there and 10 feet there. And we're told at 5 feet we have 1,000 pounds. And is that what I have going on there? So we've got a pin here. I've got a roller there. So I've got that. I've got this force, 1,000. And then what's going on with this pin? Well, over here we said CY was going up. That means CY has to go down here. Newton's third law. If this is holding this end up, it's pushing down on that. Okay, it's like the hitch of a trailer. If you're pushing up on the tongue of the trailer with the bumper of the tow vehicle, the trailer is pushing down on the bumper of the tow vehicle. Okay, so these reactions are equal and opposite. Okay, so we have CY acting up. So over here we have CY acting down, which was 475 pounds. And then CX is to the right. So over here we would have to put it like this. Now that's not a big deal because it's 0, but if it's non-zero, then it becomes a big deal. So it's going to the right here. I put it to the left there. So very important. As I bring those forces over, Newton's third law, equal and opposite. Okay, well, with that then, I should be able to, I'm looking for this guy here, right? So what's a good strategy on that? Sum of the moments about A. I don't know A. I'm not looking for A. So let's sum the moments about that point so we don't have to worry about it. I have 1,000 times 5 minus B times 10 plus, apparently I'm going that way as positive, right? This is going to rotate clockwise. This one's going to be clockwise. That's counterclockwise. So I have 475 times a distance of 20. This one then intersects it. And a lot of times we would call that distance negligible in there, whether we're summing it about the bottom of the beam or the middle of the beam, unless we're told otherwise. If they give us the dimension, then they're looking for us to deal with that. The dimension has not been given, so we'd have to assume that it's negligible. It's a moot issue, though, because that's 0. So we could say that B is equal to 5,000 plus 475 times 20 divided by 10. So we come up with 1,450 pounds. It's positive. We drew it up, so we would expect it to be 1,450 pounds up. How do we do here? 1,450 pounds up. Right there. Answer B. So answer B and answer B. Not very creative solutions. Okay, you might say, well, this is getting fairly large. How do we all of a sudden go from a few hundred pounds to thousands of pounds? Well, anytime that you have a cantilever like this, a 10-foot cantilever, you're going to get tremendous load. And in fact, I'd have to run through it, but it'd be a good exercise to find out what AY is. You may get a negative number. Probably not. That's a fairly large value there. But I will tell you that AY is going to be a lot less than the B value there. So, good. We'll finish up then with the last problem. So 9. Given the truss with the simultaneous loads shown, so these loads are placed on it all at the same time, assuming that members of negligible mass pin connection, so that's screaming truss. Okay, so don't get sidetracked with frames or machines. How many of the members are zero force members? Okay, so they didn't even tell us the load, so they're probably hoping that we don't spend the time to do a really rigorous analysis. I mean, if you wanted to, you could put some loads in there, but let's see if we can work our way through here. Typically, where you have an intersection like this can be a big deal. So if I do a free body diagram at that guy, I'd have something like this. And something like this. This is point H, and then something like that. That's at right angles. Even if it weren't at right angles, I have no other loads, so I know this has to be 0. Okay, so that's a zero force member, so let's keep tally. There's one of them. Now, if that's 0 force and I go up and do the same thing at B, what do we have going on at B? I have compression here, I have compression there, so AB is in compression, BC is in compression. We said this one was 0, so I'm not even going to draw it in. And then what would this be? Well, it's got to be 0 too, for the same reasoning. Okay, even whether it's at a right angle or not, as long as it's not in line with these, it's got to be 0. So there's another 0, 2. Let's see, this is confusing. So let's go back over here. So essentially I've done free body diagrams at these points. At F, what do we have going on at F? Well, I'm going to have GF and FE, and then this one. I don't know whether it goes down or up. I guess over here we said it went up. 0. So that's 0, isn't it? Now, before I decide that, well, D is the same as B, we have to be really careful with that one. I'd better add to my tally. If I look at D, what do I have going on at D? There's CD. There's DE. I've got 0 there. And I'd better have something. This had better be not equal to 0 because I have this load, right? Okay, so this has to be non-zero. This is not 0. Okay, so then when we get down, if this is not 0, then this one would have to be not 0 also, wouldn't it? Okay, so I think we've exhausted the zero force members. There would be 3 of them. The answer would be C. Okay. Okay. I think we're good with that. I guess the other one would be I guess we could assume that they were zero loads. So we'll say assume non-zero loads. Okay, we could argue that. A lot of times the test is not a good time to go do something weird and then try and argue your way out of it. But anyway, we'll try and keep the wording a little tighter on the exam that we grade. Anyway, I think that gets us to the end of this test. It took a little longer because I showed you some different ways and some different options. Tried to explain things a little better. You should be able to sit down with this thing on a clean sheet of paper and hammer it out in about 40 minutes or so. So print it out and give it a try. Even if you've done it before, see if you can do it faster. See if you can do it better. Go back, practice homework problems. It's just like a sport or a musical instrument. Practice, practice, practice. So thank you for watching and take care till next time.